Hello, we're in the multiple linear regression setting, and we're going to prove the Gauss Markov theorem, which says that the least squares estimates of betas are blues. And a blue is the best linear unbiased estimator. So here's the setting. So here's our model, our linear regression model, or multiple linear regression model. And our assumptions is that the mean of the epsilons, or the errors, are 0, and the covariance matrix is sigma squared I. Now we're also assuming that the rank of x is k plus 1. So that means x is full column rank, because this beta is beta 0, beta 1, all the way to beta k. So there's k plus 1 betas here. And so the number of columns is k plus 1. We have to assume that it's full rank. We don't have to assume, but in multiple linear regression, we do assume that. So now the optimal unbiased estimators. So whenever you see optimal or best in statistics, you have to learn what that means. Like, what does that mean? And it means the smallest variance, right? Now a blue is the best linear unbiased estimator. A UMVUE is uniformly minimum variance unbiased estimator. And you think about it like this. If this is all the estimators of theta, and then we can group the unbiased ones together, and we can group the linear ones together, and then all other estimators all fall out here, right? Now if we just want to find the one with smallest variance, it's actually a silly estimator, and here's why. Whatever theta is, we're going to estimate it with 10, the value 10. And what's the variance of a constant? 0, right? So just having smallest variance is actually not a good property, right? Because we can always use a constant estimator and come up with the variance of 0. So we have to add criteria like unbiased. And so on average, our estimate is going to be equal to the parameter that we're estimating. Linear is nice because linear functions are so easy to handle, so convenient, have nice properties, and so they're nice. Now we want to restrict ourselves to linear and unbiased, so that's in here. And so what a blue does is it tries to find the estimator in here that has the smallest variance, and that's called a blue. Now a UMVUE it's unbiased and has smallest variance. So it could be over here or it could be here, right? So the UMVUE is could be smaller than the blue. Okay. So in this video, we're going to show the least squares estimates are blues for beta. And in another video, we're going to show the least squares estimates are UMVUEs, right? So it turns out that the best is in here. It's both linear and unbiased, So before we start, I want to introduce a definition here. Let's let L be a k plus 1 vector and let it be known. And then we want this function, L prime beta. It's estimable if an unbiased linear combination of the y's exists. And that means that the expected value of ty is equal to L beta. If this is true, then L beta is called an estimable function. Okay. Now, when they introduced the Gauss Markov theorem, or showing that the least squares estimates are blues, they don't talk about estimability, because it turns out that when you have full column rank, all these betas are estimable. Now when we get into design of experiments, and the model looks exactly like this, generically, but the x's are not, this design matrix is not full column rank. And then estimability plays a huge part of what we do. And so really I could have left this out, the estimability part out, because it's always estimable, but I'm sort of kind of foreshadowing what we'll have to do in design of experiments. So one quick theorem is that if this linear combination of the betas is estimable, it is estimable if and only if there exists a t such that this L is equal to t prime x. So the necessary part, or going to the right, so we assume this is estimable, then there exists a t such that it's unbiased, right? But the expected value of t, y, is this, and the expected value of y is beta x beta. And now since this is true for all beta, it doesn't matter what beta is, that implies that L prime is equal to t prime x. So that shows that this has to be true. Now let's go to the sufficiency part. So let's assume this is true. Then L beta, which is equal to, you plug this in, which is this, but x beta is actually the mean of y, and that's constant, so we can take it in. It's this. Well, we just found an unbiased estimator of L beta, so it's estimable. So this is an if and only if. And that's all we're going to say here. It's going to become much more important when we do design of experiments. So theorem 2, if L beta is estimable, then L beta hat is a blue for L beta, this linear combination. Now one thing, the linear combination, this L could have a 1 and then the rest zeros, and then it isolates beta 0, right? So beta 0 is estimable. And this L can be 0, 1, and then the rest 0, and then it isolates that beta 1 parameter. But this is only true if L is in the row space of X by the previous theorem. But when we have full column rank, then we can always find that L. There's actually, there's whatever the rank of X is. So in our case, it's k plus 1. So there's k plus 1 independent vectors that in finding this combination, and which means that we can, there's k plus 1 independent vectors, means we can isolate each one of those beta parameters. So in design of experiments, it's not true. We can't say that the least squares estimate for each beta is a blue, but this linear combination for estimable functions is a blue. In much more detail on that when we get to design of experiments. So first, the expected value of L beta hat, and this is our least squares estimate for beta, is this, which is this. So it's unbiased. So this is an unbiased estimate for L beta, which shows that L beta is unbiased, or L beta hat is unbiased. So now let's let A, right? And this is important because we're trying to find a blue, best linear unbiased estimator. So you first have to show it's unbiased, and that's what we did. So now let's let AY be another unbiased estimate for L beta. That says that the expected value of this linear combination, which is this, but we're saying it's unbiased, so this expected value is L prime beta. But so these two have to equal, and this is true for any beta. So that says that L prime is equal to A prime X, right? It has to be. So now let's look at the variance of A prime Y minus L prime beta hat. And the variance, we can take that out front and transpose it out back, the same with this L, and we get this. Now the variance of Y is sigma squared I. The variance of our least squares estimate is sigma squared X transpose X inverse, and that's from a previous video. The properties of the least squares estimates. Now, here we can factor out a sigma squared, and we get this, right? Now, we also L, since L is A prime X, we plug that in here for L. Now we left factor out an A transpose and right factor out an A, and we get this. And then we rewrite this as the hat matrix. And now instantly, since this is a perpendicular projection matrix, more specifically it's idempotent, we can instantly say this has to be greater than or equal to 0, because if this is idempotent matrix, it's always positive semi-definite. But let's show that. Since this is idempotent and symmetric, it's equal to this, right? That times itself. But then we can think of this as V, and this vector is V, you know, where V is this vector. But then this says that, you know, it's sigma squared, the sum of the VI squareds. But whenever we're always adding up positive or non-negative things, so this has to be non-negative, right? But remember our first one, we started with this, so that implies that the variance of our least squares estimates is always smaller than this, any other unbiased linear combination, right? Could be equal. We could find something that's equal to it, but we know that this definitely has the smallest variance. So it's a blue. Now, one thing we want to show, though, it's kind of unsatisfactory that there may be some that are equal to it. But let's show that it's unique. Let's show that L beta prime is the unique blue for L beta. Here's the proof. So let's let AY be another unbiased estimate for L beta. Assume the variance is equal to the variance of this blue, the L beta hat, right? We're assuming that it's equal. This is true if and only if, right? So if these are equal, that means, you know, that this is an equal sign, and it's equal to 0. So that says V prime V is 0, right? And this is true if and only if V is 0, right? Because they're vectors. But V is 0 if and only if, you know, we replace what it is. I minus HA is 0. And then you multiply that in, and then take the HA to the other side. So this is 0 if and only if A is equal to HA. But this is true if and only if A is equal, we just expand the hat matrix. And this is true if and only if, remember we said that AX, A prime X is L prime, right? So we put L there. And that's from Theorem 2, so there's an L there. So note that if we so this is our unbiased linear combination. And if we plug in what we know for A here, remember this is A transpose, this is just A, so you have to take this transpose. And so you get this, the transpose, this, and X transpose. But this right here is our least squares estimate for beta, and that's L. So this, if it's unbiased and has a variance equal to that of the blue, well, it has to be the least squares estimate. And that proves uniqueness. Well, that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.